Hi everyone. I hope that the exam last week was reasonable and that you all feel pretty good about it. Um, so the graders are working on it, and we'll get those scores back to you, as well as some of uh, the past homework assignments and the exam one score, which I've been meaning to post for quite some time. So for today's lecture, we are going to keep it pretty short. As I mentioned, these videos, you can expect there to be more of them, and you can also expect them to be shorter than the average lecture. We only have two chapters to go over. Chapter 5, which is Induction and Recursion, and then Chapter 6, which is Permutations and Combinations. And then the rest of the classes will be supplemented by other content that I feel is just good for computer science majors and software engineers in general, and the art of software development as a whole. So we'll get more into programming examples and so forth. But for those of you that are strictly concerned with your grade, Chapter 5 and Chapter 6 are the remaining content. And the notes that I'm including in these videos, I will make available. And I'll include some of that other content as well. Okay, so let's jump into it. The bane of my undergraduate mathematics experience and programming was induction and recursion. So from a formal standpoint, I will struggle to really handle inductive proofs. It seemed like circuitous logic. So it felt like you were assuming, the conclusion, and nothing ever really happened. So what I missed as an undergraduate, I hope to rectify now as your instructor. Uh, and then when we get to recursion, we'll include several programming examples, and hopefully the examples will make it a little more bearable. And for those of you that want to codify those examples, I would highly encourage you to do so, as um, the the action of it, the activity of programming and putting into action something that you know should work, will kind of help reinforce the fundamentals of programming. So uh, it's always good to take an active approach to your lessons. But anyway, that comes later on. Right now, we have to suffer through mathematical induction. So the content is covered in section 5.1 of Rosen, the textbook, uh, and it's really quite simple. So I'm hoping to keep it simple and not go past the point of what's beneficial to see. So we'll go over three examples and the definition as well. Uh, and so the idea here is that with mathematical induction, you can prove a single case, and then you can take advantage of the ordered nature of the natural numbers, the countable numbers. And whenever you prove something for that base case where n equals 1 or n equals 0, um, if you can then prove that anytime you have it something that is true for some value n, uh, it necessarily implies that it's true for n plus 1. Well, that's really all you have to do, right? So you've proven it for some minimal value, and then you've shown that you can count forward and have it always be true, right? So if it's true for n and it's true, and that means that it's true for n plus 1, well, by having that base value, then whenever you tack on 1, it's now true for n equals 2. And when you tack on 1 again, it's true for n equals 3. And as a result, it's true for all of the numbers greater than n, up to any limiting assumption if you've made it, or in the cases that we'll see today, it's true for all of the positive integers once you've reached that point. Uh, so so it's really just two steps, right? We'll expand it to where there's three, um, but you can think of it as just being two. There's the base case, and then there's the inductive step. So let's get into the examples, and hopefully that'll remove some of the abstraction behind this notion. Okay, so the first example is a sum that we've proven before. I think we used, I discovered it was Gauss's proof, not Euler. I've been attributing that to the wrong mathematical genius. So my apologies to Gauss for that. Okay, so the sum over the first n positive integers, we've previously shown that constructively that sum is equal to n times n plus 1 over 2. And now we can use induction to prove it. So whereas previously we'd constructed it and we had a constructive proof, now we can say, okay, well, if you give me a solution, then I can prove it using mathematical induction. I have no idea how we got there. Who knows where this magical wisdom came from, but I can show you that the answer is correct. And that's really all that mathematical induction claims to do, is given some magical solution, we can verify that yeah, the magic was true. It worked, right? So, okay. So, as I mentioned, there's a basic step, and then there's the inductive step, and sandwiched in between is the inductive hypothesis, where we just assume that it works for some value k, and then we show that when it's true for some value k or some value n or whatever your favorite variable is, then when that is the case, it implies that it's true for the next number. And so the combination of that basic case and the ability to count forward proves it for all of the natural numbers. So here in the basic case, we show that our sum is true whenever n equals 1, that the sum from 1 to 1 is 1. And then it's also true in this form, the magical form that we're verifying, where it's 1 times 1 plus 1, which is 2 over 2 right here, and that reduces to 1. So it's true for some basic case. And now we want to show whenever it is true for some integer, some positive integer, that it's true moving forward as well. So we start by assuming that we have some value k, which is true, and then we want to show that implies k plus 1, or it's true for the case where of k plus 1. And that is the inductive step, right? So this is our second actual working step, right? So we assume by the inductive hypothesis that it's true for the sum over the first k values, and then we show that implies that it's true for that k plus 1, k plus first value. I'm not really sure how to say that, but okay. So it now runs from 1 to k plus 1, and then we separate it, and we show, so this sum is 1 plus 2 plus yada 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 up to plus k plus 1. And so we pull out that last term, and we reduce it to our new information plus the previous information, right? Well, this previous information was given by s sub k, and we're assuming that by the inductive hypothesis, we're assuming that to equal this, right? So then when we have that this substitution is valid and it's true, we can now construct that next value, and so it reduces to a simple equation at this point. Well, you multiply the top and bottom by 2, and now you have a common denominator. You can push them together, and now you have something that is k plus 1 times k plus 2 over 2. Well, we wanted to prove that this summation index, which coincides with the upper limit of our sum, right? We wanted to prove that you can just pull this out and magically stick it into the formula for n. So when n equals k plus 1, we would expect the solution to be k plus 1 times k plus 1 plus 1, which is k plus 2. And we get this. So we verified it, that if you give me a working solution and I increment it by 1, then our formula still holds. Well, we constructed that working solution in the base step, right, the basis step, and then we showed that, well, if you have one solution, you can get to a valid form for the next integer, and then just you from there, the fact that there's always the next integer implies that there's always that this is true for the next value as well, right? Like we've constructed it in this counting form. Okay, so let's take a look at another example, and hopefully this awful subject will seem slightly less awful here in a little bit. Okay, so now we're looking at another sum, S sub k, right, where the sum runs from n equals 1 to k, and we're putting it in the formula for odd integers, right? So 2n minus 1 or 2n plus 1, those are both ways to construct odd integers, right? But if you start with n equals 0, then it's 2n plus 1 to get 1 as your first term, and then it will correctly compute 3, 5, 7, and so forth from there. If you start with n equals 1, as I like to do in these summations, but I don't always, right? But my preference is to start with n equals 1 and then have it run to k. Then the form for constructing the positive odd integers is 2n minus 1. Okay, so given all of the odd integers, 1 plus 3 plus 5 and so forth, up to some value 2k minus 1, the claim is that the sum of those first k odd integers is k squared. So the first 3 odd integers would be 1, 3, and 5. And if you add them up, 1 plus 3 is 4, and 4 plus 5 is 9. And we've added the first 3, so we did get 3 squared. 3 squared is 9. So we want to know whether or not that's some oddity, or if it's something that holds going forward. And so we can use induction to prove this claim, and it is true. So whenever we let k equal 1, then this reduces to just summing over one value, one odd number, and it's 1, and 1 is still 1 squared, right? So we have a basic case. We have some foundation upon which to build. And then we say, okay, so let's assume that this bold claim is true, and then if that's true for the first k numbers, right, then it would be true for that. Then if we can show that it's true for one more, and it's always true for one more, then we've shown that the claim overall is true. So let's see if given k consecutive truths, if we can prove a k plus first truth, k plus 1th truth. There's got to be a way to say that. Okay, so then the sum over the first k plus 1 odd numbers we would note it in this fashion, right? And that's really just adding 2k plus 1 to our previous sum, which looked like this, right? From 1 to k, so the first k odd numbers, and then one more, right? And so again, we've combined it into the new information plus the previous information, and the substitution is the inductive hypothesis. It's the inductive step, or it's a necessary part of the inductive step. And so we can make that algebraic substitution following our assumption, right? Our assumption here. And so if you can give me k consecutive values where this is true, then we can see just by adding that 2k plus 1th number to that previous sum, so that k plus first, k plus 1th, k plus 1 odd number. I'm going to figure this out, perhaps not in the length of this video. Anyway, so you add the next odd number to the previous sum, and you get this. Without any magic, right? So you have k squared. We'll just move it over to the left so that it's sorted by the degree acting on k. And then 2k right here, and then 1. Well, this is k plus 1 squared. Well, that was exactly what we claimed, is that that sum would result in k plus 1 squared. And again, we're not using circular logic here. It is actually constructively finding that next term, or finding that it is true for a next term. So given a truth, we can show that it's true for the next odd number in the sequence. And because we've shown that it's true for some minimal value, and it's true for the next value, the fact that the integers run on forever shows that it's true for all of the positive integers, beginning with that minimal value, that base case that we proved at the beginning. Okay, so last example, and then we'll probably go through the rest of Chapter 5 either on Wednesday or Wednesday and next Monday. But this is the last example for today, trying to keep the video short and hopefully rewatchable, hopefully tolerable. Okay, so this last example, we're running over the first k powers of 2, where we consider that first power of 2 to be 2 to the 0, right? So in order to do that, we start with n equals 1, as is my typical preference, and we get to 0 by raising 2 to the power n minus 1, right? So, okay, so now this is the sum that we're looking at, and we claim that this sum will always equal our subindex here, right? So if we're summing over the first k powers, beginning with that power 2 to the 0, the first k powers of 2, that sum will equal 2 to the k minus 1, right? So basically 2 to the 0 is 1, which is 2 to the 1 minus 1, right? That's 2 minus 1. The sum of the first two powers would be 2 to the 1 plus 2 to the 0, which is 2 plus 1, and that's 3. And so by this form, that would be 2 squared minus 1 for the summation, and that's 4 minus 1, which is also 3, right? So the pattern holds so far. And if we were to put it in binary format, which I believe is how we demonstrated this earlier in the semester, then we would see this is inherently true, right? Like if you add one more, then you get 2 to the k. Whenever you have k bits set, right? The k least significant bits set, you add one more, then you get 2 to the k. So then having all of those bits set is equal to 2 to the k minus 1. Okay, probably a little easier to visualize on a whiteboard there than just in your head. But okay, getting back to the problem before we get off on too much of a tangent, we're focusing on the inductive proof of this. So given this sum over the powers of 2, we believe that it will add up to 2 to the k minus 1, right? So again, as is hopefully becoming a bit intuitive, we start with some basic case, right? And here we let k equal 1 for our base case. So from n equals 1 up to 1, we have that our sum of those powers, right, which at this point would just be right, yeah, which would just be 2 to the n minus 1, so 2 to the 1 minus 1 is 1, and we show that is also equal to 1, and then using the other formula, this formula, it's also equal to our formula, so it holds in that base case where this is k equals 1 here, then it's 2 minus 1 is 1, right, as shown here. So now the inductive hypothesis, which is, again, part of the inductive step. So I have it broken out here as 3 steps, but it's really 2 steps. There's the base case and then the inductive step. So then, again, we show that our sum, which is given by definition, right? So we have some sum, and then we have an arbitrary sum, right? And then we have a claim that we have some closed form solution for it, and we're verifying the closed form solution, right? So we put it in the definitive form, and then we show that we can recover from that and the inductive hypothesis that we can recover the closed form. We're already assuming this form, s sub k equals 2 to the k minus 1. And we show that if it's true for the first k, and we add one more term, a k plus first term, that we can recover the closed form. Right? So in the definitive form, so as we have defined our sum, it looks like this. And then, again, we strip out the latest term. We strip out the new information. So 2 to the k plus 1 minus 1 would be right here. And then we've reduced the remainder of our sum to, again, the previous information, the already known information, what we are already assuming to be true in this form. By assumption, by this inductive hypothesis, the other sum, the first s sub k terms, is equal to this, right? So this has a definition, right? And so by definition, this is equal to this. By assumption, this is equal to this. Okay, and then this term, right? So here it's 2 to the k. Here it's 2 to the k plus 1 minus 1. Well, the plus 1 and minus 1 cancel out, and so that's 2 to the k. And so we have this, which is the new information, and this, which is the previous information, and then now we simplify. Right? So add 2 to the k plus 2 to the k and minus 1. Well, minus 1 we leave separate, but this, well, it's 2 of the same value, so it's 2 times 2 to the k. But this is the base value, right, in a power. So we increase the exponent by 1 because it's the same as the base, this new term. And so we get 2 to the k plus 1 minus 1. K plus 1, k plus 1, 2 to the k plus 1 minus 1, or 2 to the n minus 1, or whatever. And that's exactly what we were trying to show. So we've done it. Later we may briefly talk about strong induction. Maybe. I'm not convinced that it's any greater benefit than induction as a whole, right? Like you have some base case, and then you have an inductive step. And then strong induction just assumes it for some value other than n equals 1. Well, that doesn't really matter in my mind. Like the principles are exactly the same. I'm not sure why they created some new term for it. And then recursion we will definitely cover as well. That's it. Hopefully it's not too terribly painful, and if it's confusing, and as I have already admitted, it was definitely confusing for me as an undergraduate, then watching this over a few times will help simplify it a little and give you a little bit better intuition for what's going on. And then the homework problems that I'll give you on Wednesday hopefully will reinforce that. All right, have a great day, and please feel free to email me if you have any questions. Thanks.